Okay. Okay, so I'm going to start off with illustrating the premise of the paper through an example. So if you imagine that you are hiking in the mountains and it's sunny, and then all of a sudden there's an unexpected change in the weather. You need to be able to distinguish between a regular weather fluctuation, if it's just a passing cloud, between that and a significant weather event such as an approaching thunderstorm. Because although in both scenarios the weather is currently less predictable, they should have opposite effects on your behavior. So the appropriate response depends on accurately assessing the cause of these incoming clouds. So we have if the unexpected change is caused by just a regular weather fluctuation, this is called stochasticity, then we would continue with our current course of action. There'd be no change in behavior. Whereas if the change is caused by a thunderstorm volatility, then this requires a quick response, and the earlier estimations of the situation become irrelevant. So just to summarize, there's two types of observational noise, and what we predict to be the cause of noise out of the two influences our decisions in the face of uncertainty. Does that example make sense to everyone? Yeah, cool. Okay, so this type of error-driven learning relies on two key factors. So a prediction error, which is the difference between our prediction and actual incoming sensory input, what we're actually observing, and then also a learning rate, which determines the weight assigned to new information. So this is what is influenced by the statistical properties of these two types of noise in the environment. And I've have it outlined here. So higher volatility is thought to increase the learning rate because it reduces the usefulness of old information, increases the usefulness of new information, and then there's higher stochasticity, which decreases the learning rate because the present outcome provides less information about future outcomes. I'm going to use another example to explain that bit on this side. So if you think in response to a surprising outcome, when you're playing a game, in response to a surprising outcome, if the outcome was just based on bad luck, you would stick with your decision strategy, and that wouldn't cause no increase in the learning rate, decrease the learning rate. Whereas if there's a change in the rules, you might change your decision strategy, and that would increase the learning rate because it reduces the usefulness of old information. You're no longer basing what you currently would do based on old information.
Oh, Katie,
Yes.
am I thinking about this right that it's like a sort of decreased things learned per second? Like if you're learning, like if there's more randomness, your learning rate drops because there's just less learning per second going on because things are more random. Whereas if something's very predictable, you're learning at the amount you learn per second is higher. Is that what's meant by like rate here? Sorry if that's a dumb question.
No, so when you say randomness, so it would depend what is causing the noise in your current observation. That's what this paper is based on, a type of error-driven learning, whereas if it is observational noise that is volatile, then it would increase your learning. Whereas if it's stochastic, then it would not increase your learning. Does that answer
Oh,
your
I get
question?
it. Yeah, that makes sense. Thank you.
Okay.
So is
Yeah.
that is the example of the rain?
Mm-hmm.
Would a better example, I mean, because there's not a difference between the amount of rain that's a cloud and the amount of rain that turns into rain, other than the amount of rain. Would a better example have been, I'm throwing a dice, and option one is, and I haven't hit six for a long time, option one is I'm just being unlucky, option two is the dice are loaded. Like, isn't it more of a structural change in the system that's generating the information that you're receiving?
Well, I guess in regard to the weather example, um, if there, I guess it's more like if there's a slight change in the weather that wouldn't cause you to change your behavior, you would just keep going. You would just kind of ignore it. Whereas
Yeah.
if it suddenly started raining loads and there were, you know.
Yeah. Keep going. We could come back to this. Keep going with the
Okay. So this perspective, this like dissociation of these two types of observational noise has influenced hierarchical Bayesian modeling of learning. So similar to predictive processing, where you have the prior probability distribution and you compare that to coming sensory input, and then any discrepancy causes a prediction error signal, which then informs the posterior probability distribution. And there's also the precision weighting, which is kind of akin to the learning rate, which is going to weight how much you're using the current input to inform your learning rate. So these authors have stated that there have been previous experimental studies that have demonstrated humans' adaptability to either types of noise, but these have typically been manipulated or modeled in isolation from one another. They've not really been modeled at the same time. So the rationale that the authors provide for this paper is that a more challenging computational question that has remained unanswered is whether and how organisms infer the true cause of noise, which would sometimes be a mixture, or is most likely to be a mixture of volatility and stochasticity, really hard word to say, when both factors are unknown and potentially changing, because in real life, they are easy to confuse and they are both making observations noisier. So, and all we have to rely on are our observations over time to dissociate these factors. So yeah, this is building on the author's work from a few years ago. They published this paper, which was a computational modeling paper. And they showed at a computational level that the statistical difference between these two is that volatility increases the autocorrelation, while stochasticity decreases the autocorrelation. I'm going to explain more about that in a few slides, but I just wanted to highlight here that they have previously shown that it's computationally plausible to distinguish between these two types of noise. So that now what they're doing in this current paper is comparing this model to experimental data. Any questions? No. Okay. So I'll go on to explain the task in the current paper. So experiment one and an N of 223, and they used a behavioral prediction task. So there's a illustration here. On every trial, participants moved their bucket to catch bags of coins dropped by a bird. This bird is invisible, the participants can't see it. So they instead have to estimate the position based on the location of dropped bags on previous trials. And once the bag appears on the screen, they can't move their bucket. And I will explain about the block order. So this was a 2 times 2 factorial design. meaning they could systematically manipulate volatility and stochasticity at the same time. And the design was divided into 4 blocks. The values of each were fixed per block, but the participants were unaware of the true values. So for volatility, the participants were instructed that the bird moves noisily on a trial by trial basis, and that's providing noise whose variance is volatile. And then they were also told that the depending on the wind, the bag might fall right under the bird, in front of it or behind it, which is inducing noise whose variance is stochastic. And this allows for manipulation of both types of noise at the same time. And then, yeah, Tom?
Oh, I'm so sorry. I interrupted you in the middle of a sentence there. Do you want to finish?
I was just saying that participants were told that they would be playing against 4 different types of birds in 4 different weather conditions. That's what's producing the 2x2 factorial design that I showed.
Yes. I'm so sorry, just because I'm a little bit slow. Could you maybe explain why the bird moving noisily introduces volatility versus the bag introduces stochasticity?
Yeah, so
It's not a very accurate. It's annoying me because birds move. But I think you've just got to imagine a flustering bird like this.
yeah, so it's never going to be in the same position than it was the trial before. So you can't just participants couldn't just leave their bucket where it is. I don't know if this slide helps. So in the small block, the bag would fall right under the bird because of low wind, and the bird doesn't move much trial to trial, so it's moving a little bit but not loads. So you can kind of induce where it's going to be based on where the bag was dropped before. And then in the large stochasticity and small volatility block, the bird doesn't move much, but the bag would fall either like quite a bit in front or quite a bit behind it due to strong wind. Does that help, Tom?
So is it that, so I'm thinking back to the weather example where like the volatility is this sort of small scale fluctuations that will change quickly. Whereas is it right that stochasticity was more indicative of like an overall trend?
No, the opposite, the other
Okay,
way
well,
around. Yeah,
so maybe I'm missing like how the
how the
sorry,
bird.
probably everyone else is getting this, so we can move on.
No,
No.
probably not. I think it may be a bit confusing.
So basically there's the position of the bird, yeah, above the screen. And the bird is moving slowly from one to one and then dropping coin. Yeah. That's one source of variability in where the coin appears on the screen. And then the other is every time the bird drops a coin, it will randomly get blown this way or that way by the wind. And that's the other source of variability.
But the participants cannot see the bird, can they?
No.
So
No.
how are they supposed to know, like, where is the money gonna be dropped or the bag gonna be dropped?
Yeah, that's what they're trying to estimate. And within each block, the value of each is fixed, so they will be able to learn over time if there's a high amount of wind or low amount, if the bird is moving around a lot or if it's not.
But I assume the bird moves in the same direction all the time, or because
Yeah,
otherwise it's just impossible, isn't it?
yeah, I assume with there being small or large volatility, yeah, so it will be moving like, I guess, like along the screen and then backwards. It won't be jumping around. I guess that is the only way you could infer. Like apart from this drawing, that's all I know about the
Daisy, do you think this could be modeled by like two sorts of frequency? One of them, like the movement of the bird being like the slow moving frequency, or sort of the position on an x-axis like goes up and down in a slow way as the bird moves. And the other type of I think volatility is like higher frequency movement, but from that like low moving position already. Like I don't see how that's different from a type of noise that would be like white in a sense that there's like low moving values, but on top of that, fast moving values. And then it's just a matter of what's the like ratio between the high versus low frequency.
Yeah.
Only high
So-
frequency can be everywhere at any stuff, and if it's low frequency only, it's like it's moving over time, but in a like predictable manner, sort of. Let's say there's no wind and just the bird is moving. You see what I mean?
I get what you mean about the ratio between the two types of observation noise, because they do talk about that a lot in this paper. But I don't really follow what you said at the start about how else it could be.
It's not just low frequency versus high frequency there, Pierre, because it's also about the autocorrelation, yeah? So it's what they said earlier. So if the bird is doing this, yeah, then it'll be gradually moving up in a way which isn't just a slow moving rate of change, it's also continuous, yeah, so it reduces. So that type of noise will have a very high autocorrelation, yeah. The bird is a terrible thing because obviously birds move very fast. You want to be thinking about like a.
Can I ask you a quick question?
Yeah, of course.
Okay. So what information does the noise of the bird give us about whether the bird is going to drop the bag or the location of the bird? Like what information is noise? What type?
Yeah, where they're going to drop the bag, because you're trying to catch it in the bucket.
Yeah, but the noise is telling you a location.
So that's what participants are trying to, I guess, navigate through each block. You know, there are these additional parameters, and they're trying to catch as much money as possible in the buckets. But it's not always going to be as straightforward as it's dropped it like here. So, you know, so that's what the different types of noise are inducing different amounts of uncertainty.
So is it right, the stochasticity controls, like if there's high stochasticity, the bird moves a lot but the same amount each time, or a lot but jitters? And then is that's the volatility.
Yes.
And
Yeah.
then the stochasticity is like when it drops, the bag might go like any kind of weird direction.
Yeah. If there's a large amount of stochasticity, it will either fall because of the wind, that's the wind parameter, then it will drop behind or in front of it. It won't drop directly under it.
That makes sense. So one is like very, sorry.
Yeah, sorry, go on.
So one is quite predictable, I guess, and the other is like you know it's going to move a lot. The bird is going to move a lot, but it'll be in like one direction, and you can predict easily where the bag is going to fall. Whereas with large stochasticity, that's way more uncertainty because you just don't know which way the bag is going to fall.
Yeah.
Or how much as well.
Yeah, so that's what this task is based on a model, that is saying exactly that volatility is what will increase the learning rate, whereas large amounts of stochastic noise is not going to increase the learning rate because it is more random. You're not going to induce anything from that.
That makes sense.
Maria, this is quite for your PhD.
Yeah.
Maria.
Oops, sorry.
No, sorry.
No, go on, Tom.
I think something, sorry if everybody else gets this and we can totally move on. Something that I don't quite get about like large volatility. So the volatility controls the amount the bird moves. So why would having a large volatility be different from having a small volatility? In the sense that providing the stochasticity is small, you should be able to predict where the bag's going to land regardless. Am I just missing something really big there? So my idea is that the learning rate should be the same for large and small values of volatility, but obviously that's wrong.
I think if we move on, maybe that will clear.
No,
Yeah,
I
of
think
course.
the answer to your question is it's how. So if you've clocked that there's high volatility and the bird is moving a long way that way, you will systematically move your cut more between trials. Yeah. Whereas if you've clocked that there's low volatility, then you will just move your cut a little way. Yeah.
Oh, okay. Yeah, that makes sense.
The
Thank
volatility, if you work out what the volatility, I mean, if I've understood it quickly, if you work out what the volatility is, then you can make accurate predictions, but you just need to work it out. Yeah.
I think, Katie, if you can open the stuff in the chat, I think that's exactly what this plot shows. Like, if you see the birds, like let's say X position, I don't know if you can see the chat, but oh, sorry, never mind. If you need to put it, there's this plot, yeah, showing stuff.
Oh God, what have I done? I can't see that right now.
I can. This makes it look like low frequency versus high frequency, though, Pierre.
Yes, exactly. That's my point, though. I think that's just high and versus low frequency. And I think I told that to Francesco last time, and he said, yeah, maybe, which was quite not satisfying.
I love the owl. It's like there's a really bored camera director. For those of you who can see it, it's like I'm bored of what Pierre is saying right now, so I'm going to focus on Gio's left nostril.
I don't know that.
Gio's left nostril as Pierre was talking, which distracted me. Pierre, let's say that again.
No, just yeah. Francesco didn't have an answer for this. Just looks like high versus low frequency, as in volatility is low, like slow moving waves, and noise is just high frequency noise. Like this seems like it's just this. On the green plot on the right, you just have like a slow moving bump and a fast moving between trials at high frequency.
Yeah, I do get what you mean there.
I guess that's not saying it's wrong. It's just a different thing, maybe.
Yeah, I'm a bit overcomplicating it. I don't know. Okay.
No, I think they've got a different definition. They're slightly different definition, because for them the idea is moving. Yeah. Bird doesn't just jump from one place to another at slow time frequencies. So it's a slightly different definition, but it's obviously closely related.
It's kind of hard to explain it without playing it. But anyway. Okay, so how they have there's just a note how they've generated the noise, I guess. Different from other.
Wait, Katie, you're not showing your slide again.
Oh, I'm not sharing.
No.
You are.
Oh, sorry, me. Sorry.
Wait, Katie, can I just ask you a super quick question before we so just so that I've understood correctly and based on what Sam is saying, so there's no way that between trials the bird could have moved by a large degree. We can't, like the bird, so in high whichever is the one which will involve the bird moving between trials, the bird can't move by a big amount based on what Sam's saying. We can't predict the direction, but it will move by the same amount, or could it have jumped to a completely different location? So could it be on the right side of the screen and suddenly go to the left? We can't see it, but basically the place from where it's dropping the back, and it shift by a huge degree between one trial and the other within the same block.
Yeah, I feel like I didn't really think about this as much as I don't actually know. All they say is that what is listed here, that the bird moves noisily. So I guess that would be jumping around, but then that would be kind of difficult to infer its location, but yeah, I'm not really sure. Sorry.
No problem. I was just thinking because, like, if so, the wind, based on what they've said, the wind can never make the bag move to a much larger, like, it can never make the bag move much away from the bird. It can move it before or after the bird, as opposed to dropping directly underneath. But it doesn't seem to me that it can move the bag by a large extent. So there is a difference in that, right? So if the bird is moving only by a specific unit, we just can't predict whether it's going to move or what direction it's going to move. And the bag will never move. Oh, that's the same thing. Actually, never mind. I'm also like trying to.
No, I do get what you mean a bit. Yeah. Well, yeah. I don't know. I guess they have shown that large volatility does increase the learning rate. So obviously, participants, when they're doing this task, they are able to work out roughly or estimate the level of volatility in the bird's movements somehow, but I don't really know how without playing.
Katie, just quickly, so basically higher learning rate means less trials to get the bag?
So the learning rate is worked out on a trial by trial basis. Maybe if I just move on then explain a bit more about that, then if it still doesn't answer your question, then we can come back. Okay, I might just so they first worked out the optimal learning approach using a Kalman filter, which is a Bayesian model. And according to the principles of this model, the learning rate increases with higher volatility and decreases with higher stochasticity. This is because they exert opposite effects on the autocorrelation of observations, which I'm going to explain now. So autocorrelation is defined as the covariance between observations on successive trials over the variance of observations. And I guess, yeah, a feature of this model is that volatility increases the covariance and the variance, so it increases the autocorrelation overall, whereas stochasticity increases the variance of observations only, so it's decreasing on the autocorrelation overall. If anyone knows a bit more about autocorrelation, that can maybe provide a bit more. I think I understand it. I think because autocorrelations, if anyone correct me if I'm wrong, but is it a lagged correlation between observations? So
yeah, it's just. So who's going to say?
Oh, I was going to say, but probably it's better if you say.
Well, I was just going to say it's just the correlation of the variable to itself at time intervals, yeah. So I correlate the variable with itself, yeah. So I've got the same variable against itself, yeah, which is by definition 1, and then I move it one time series, and I repeat the correlation. I remove it another time series, repeat the correlation, and so on, yeah. And if it's a very slow varying time series, then the correlation of the variable to itself is at 1 at time 0, and then when you move it 1, then it'll be very similar. It would also be very high, yeah. So if you get an autocorrelation plot that looks like that, you've got a very slow moving up and down variable. Whereas if you've got a very jaggedy variable, then when I move it one time series against each other, that would have a big effect on how much that variable correlates with itself. Does that make sense?
This seems almost like a different definition, right? Because it's talking about successive trials, like the covariance between successive trials divided by the overall variance, right?
So say in the egg example, yeah, your variance is the x-axis of where the egg what was it, a bag, where the bag falls, yeah. They say it falls at pixel 300 on one trial, and then it falls at pixel 295 in the next trial, then it falls at 90 on the next trial, yeah. Then that just becomes a time series of 300, 295, 290, yeah. So that's then variable, and then you calculate the autocorrelation of that variable, as I was saying. Was that
That's what I'm
something? Wait, is someone in the room talking?
No.
Oh, it sounds like it's picking up someone's voice. Okay.
Yeah. Okay. I'm gonna move on. So, just my train of thought. So this is just kind of plotting the predictions of the model. So here it's plotting how validity and stochasticity have opposite effects on the learning rate, and both factors increase the variance of observation. That's this middle plot. So although adaptive learning requires dissociating these two types of observational noise, it's possible to do this because they have opposite effects on the autocorrelation of observations. So this is the indications from the optimal statistical modeling. Okay, and then looking at the behavioral data, the learning rate coefficient was calculated by a regression analysis. The update, which is the bucket position, was regressed against the prediction error, which is the difference between where the bag is and the bucket. And then this was used as the learning rate coefficient in that block for each participant. I think so they found that this was significantly dependent on both true volatility and stochasticity. They didn't find any significant interaction effect, and they did not correlate. So as you can see from the behavioral data and the model indication, these two are in line with each other in terms of how stochasticity and volatility affect the learning rate coefficient.
Isn't it weird that they didn't interact with each other? It's like, so if the bag's gradually moving across the screen,
Yeah.
but then there's high volatility, surely it would take me longer to figure out that the bag's gradually moving across the screen. Sorry, high stochasticity. If there's high volatility, so it's moving across the screen.
But I guess they're not dependent on each other.
You are?
They're not dependent on each other, so I guess participants worked that out, I guess, which didn't cause a interaction effect. So this is plotting the learning rate coefficient across all participants. This just demonstrates that the learning rate did dynamically change over time based on their observation. So the learning rate is changing on trial-to-trial basis. Yeah, I think that's all that needs to be said for that. And then looking at the learning rate coefficient again for plotted for all participants. So although for the majority of participants, true volatility increased the learning rate, whereas true stochasticity decreased the learning rate, for around 30 participants, they showed opposite effects. So stochasticity increased the learning rate, and for around 35% showed the opposite effects in terms of volatility. So true volatility decreased the learning rate. So these maladaptive learners also generally showed reduced performance, and in their accuracy, I guess. In the first experiment, they only found a significant result for volatility learners, but then they replicated this again with around 100 more participants. So this is in experiment 2 and in 420, and they found that the performance of both types of maladaptive learners was significantly worse.
So can I just say something, Katie?
Yes.
So Lisa, are you there? I think that Al focused on you at some weird point. And Maria, this is relevant for you in so one way which I just been doing this book on concentration with Gemma, and we were talking about this idea of being more unpredictable, being predictable in your teaching style, which is what Lisa is looking at. And we were talking about, one solution as a teacher could be, some days, now I'm going to teach it like this, and now I'm going to change style, and now I'm going to do lots of visual things, and now I'm going to be really auditory. So you're constantly changing tactics, but each time you change a tactic, you do it for a sustained period of time. So you try and learn about each different thing you're teaching them in lots and lots of different ways. Like if you're teaching them a maths concept, you're trying to teach it visually, and then you're trying to teach it out loud, and then you're trying to teach it like that. Yeah. So that type of variety, from one moment to next, would be a driver of, in this model, volatility. And then there's another type of thing, which is, and then suddenly I'm going to react really unpredictably, and you had no idea what it was coming, like that. And that would be the stochasticity in the model. And we'd actually thought pretty much the same. I'm not sure, it doesn't quite map on, but it's quite similar that one type of predictability would increase, putatively, it would increase the attention of your class, and the other probably wouldn't, so that's one way in which it's relevant. Does that make sense, Lisa?
Yeah, it does make sense.
And then Maria is going to be might be looking at the same thing in terms of home environments, and the paper that I want to do next for Maria's PhD, the paper that will be good to discuss next week, we won't get a chance to, but it would be about how children learn different optimal behaviors that grow up in more unpredictable environments, and how there's some really nice modeling stuff by this guy, Willem Frankenhuis, who did some stuff about how optimal patterns of exploration in your environment are differently optimal, depending on differing levels of unpredictability. So for the point of view of a child growing up in a noisy learning environment, just as the same as an educational setting, like volatility is something you could potentially, if you can learn to predict it, you can use to exploit it to improve, how adaptive you are to your environment, whereas stochasticity is always something that prevents you adapting to your environment. So I don't know, that's just to make it a little bit less abstract in some ways. Well, it's still quite abstract. Does that make sense?
Yeah. I'm just thinking how, but maybe with the idea we had of having a more controlled setting in the lab. Well, we have to talk about it, but maybe there,
guys, that would be really good. So Maria's talking about using this new AR/VR suite that we're doing to simulate different levels of noise in the environment, and that would allow us to pick apart this. Good idea, Maria.
That would be really cool.
Do you think there's something, I mean, it's not the environment, but looking at like the volatility versus the stochasticity of the NC when someone is paying attention?
Could be. Tom's looking at in NCs, the sort of fixation component that you get relative to individual eye movements. So it's something also it's a good idea, Tom. For that.
Okay, I'll have to think about it, and we can talk.
Okay. So next they wanted to focus on these individual differences. A goal in the future of these researchers is to apply this to neurological disorders. So they wanted to build on the model to kind of work out how we dissociate between these two types of variability. So they modeled the task with a Kalman uncertainty parameter, and this encodes the ratio of volatilities to stochasticity within the block. So this is simplified, and they build on after this to kind of a more elaborate version of the model, because it doesn't really model it from the participant's perspective, it doesn't really account for trial by trial dynamics, but they first do this and then they do that in the third iteration of the model. So they quantify this using 2 individual level parameters. This gets even more mathsy now, but there's 2 values, sensitivity to stochasticity, and then sensitivity to volatility. And then there's also parameters that capture the mean and interaction effect. So there can be positive or negative for each of these values. So it can be positive, negative. The positive reflects normal impacts of stochasticity and volatility on behavior, whereas negative represents a pathological, what they consider a pathological impact of these 2 types of noise on behavior. So a model with a negative, I think this is an eigenvalue, this
Lambda.
lambda. If there's a negative lambda for stochasticity, then that represents systematic underestimation of stochasticity in favor of volatility. And then if there's a model with the same negative for volatility, then it's underestimating volatility in favor of stochasticity. I appreciate that might be a bit confusing. Does anyone have any questions about that?
And just what types of neurological things are they thinking about, like paranoia, where you're seeing patterns?
So they talk in the discussion about anxiety, and about if you have, they state that they think anxiety could be a hyposensitivity to stochasticity. So then you have it's a compensatory mechanism, like you then overestimate volatility. That's where they next want to take this to look at those kind of anxiety disorder and that, which I think makes sense. So both were significantly positive on average across all participants, and you can see here the percentage showing a negative value is around 30%, which is similar to what the behavioral data demonstrated. And yeah, here it's just going into more detail. So if you underestimated stochasticity in favor of volatility, that increased the learning rate with increases in true stochasticity. And then, yeah, same for this. I've just realized there's 10 minutes left, so I'm going to skip through this unless anyone wants me to go into more detail about it. And then they move on to say that, as stated before, this doesn't model the process from the participant's viewpoint. And if you look at these graphs, which were produced by the behavioral data, you can see that the learning rate fluctuates dynamically trial by trial, whereas the model that analysis is based on just had the parameters fixed per block. So they then produce this computational model, which is a hierarchical particle filter model. So outlined in this diagram here, the observation, which is where the bag is being dropped on trial OT, is generated based on a hidden cause, which is the bird's movement, XT, plus some independent noise, the wind, whose variance is given by stochasticity, which is ST. So the hidden cause itself is dependent on the value of the previous trial plus some noise. So photo here. Yeah, the learner should infer values of the hidden cause, volatility, and stochasticity based on, so these three values based solely on observation. And this is based, all that has to be worked out trial by trial, which is why it just says T-1 there.
Katie, can I ask a really probably dumb question?
No.
Why is it that VT-1 has arrows that go to XT-1 and to VT?
VT
So the volatility,
yeah, so it's going, so because that's X minus XT-1, so that's volatility at the previous trial is influencing
oh, the bird position
at
and the previous, yeah, I see. Yeah.
Maybe that
X is
clears
the
up.
position. Sorry,
Yeah.
Katie.
No, you go.
So X is the position of the bird, and V is how much the bird moves between trials.
Yeah, I get it. Thank you.
And then this, I didn't fully understand. I think the gist of it is that there is this model that enables a prior probability to be computed. I think it's called something to do with the particle filtering, which I've skipped over because I don't understand it, but it produces this likelihood function, which is the probability that stochasticity and volatility change on every trial. So if it's closer to 1, then the probability of stochasticity changing is higher. Where if it's closer to 0, then it's not going to change. And when they computed the correlation between this model's learning rate and the participants' learning rate, they found a significant correlation, which is validation of the model. So then they used this model to investigate signatures in the behavioral data that reveal the extent to which trial by trial dynamics of participant learning are consistent with the model. There it is. I think so that now they're using this model to look more into the effect that stochasticity and validity have on the autocorrelation. So how they did that, they looked at the product of the 2 recent prediction errors, which sampled the autocovariance between observation. This then indicates the direction of autocorrelation, so that I'm sorry, I don't understand this bit, but that then enabled them to cluster the trials into ones that had a positive autocorrelation and a negative autocorrelation.
You can't have that can't be right. There's no such thing as well, unless it's sampling. Oh, it could be actually, yeah.
Yeah.
So yo-yoing like that.
And they predicted that learning rate increases. Yeah, so learning rate would increase after a positive correlation, whereas which would indicate that validity underlied the noise, whereas a negative correlation would decrease the learning rate, and that would indicate that stochasticity is the primary function of noise. So this is plotting output from the model, which showed significant increase in, so that just showed that they found significant results for their prediction, and then they replicated these findings with the experimental data. So this is just plotting the autocorrelation, the values, and it's showing that a negative autocorrelation reduced the learning rate, whereas a positive correlation increased it.
So the only way I can think that you'll get negative autocorrelations, you're systematically each trial you're overestimating the variance and then underestimating it. Yeah. So if I've got a bird that's moving slowly like that, and then every trial I'm either
Yeah, that would produce a negative value, right?
yeah.
We're
lost on what they're actually trying to show from this, Katie.
Yeah, so I think it's like okay.
Yeah, maybe conclusion, right?
So they then looked at they wanted to look at how estimated outcome autocorrelation related to the learning rate. So the model, the particle filter model, predicts that smaller autocorrelations lead to more substantial trial by trial learning rate changes. So if there's a small fluctuation, this would have a more significant impact on the learning rate. So a slight positive autocorrelation might attribute noise to volatility, while a slight negative one in the next trial might attribute it to stochasticity. And although these are small fluctuations, it's causing a rapid shift, which is then causing a larger learning rate fluctuation. I don't really understand this bit either. And here they've shown that plotting the model's output and then the experimental data, they found similar results. Yeah.
Did you go back to the previous slide? I think
yes.
What they were saying in the last point with like the speed, this rapid shift. I think it relates to what we were saying with the frequencies initially, like in the fast moving ones. Like you're not getting a lot of information. If you know the previous position, you know it's going to be around plus or minus, and this is changing at a slow pace. But if the rate is changing fast, like about at the rate of the trials, so at each trial is going to be something different, then you, by paying attention to where the bag is, you're learning a lot of information. So I think it's a ratio sort of between the trial rate, so how much are you sampling, and how much like the stochastic volatility, like the rate at which you're changing the position randomly. It feels like it's more something about to do with the speeds, like the different rates. Are they mentioning something like this, the frequencies?
No, not at all.
Because I think Tom mentioned it, or someone else, or Sam, you mentioned it. There was something to do with like the hierarchical nature, or I think there was the example with the school. Are you changing methods every day? So that's the sort of the slow moving variable, and the fast moving variable would be, are you shouting, not shouting? Are you doing this or this? This is like the fast moving one. So it feels like it's more something that has to do with the rates of events happening more than like the origin. That's how I understand the last sentence.
Yeah. I guess I've not been thinking about it in terms of speed.
We're at time anyway, Katie, and I've got meetings to go to. Do you just want to jump to conclusions?
Yes. So so this paper, I think what I like about it is that they've shown that there's several aspects of learning that were consistent with this type of computational model that estimates the values of both stochasticity and validity, and it bases these estimations on observations solely, and then also the finding about there being two subgroups of maladaptive learners, one displaying insensitivity to stochasticity, while the other shows insensitivity to validity. I think that's a key finding of this paper that they, as I've said, they are going to take into further research. And so just to wrap up, potential applications in infant research. Why I like this paper is how you can apply it to early environments. So explore the differential outcomes for both types of maladaptive learners in predictable versus unpredictable early environments. And then, as I mentioned earlier about the compensatory mechanisms that might be at play due to a potential maladaptive learning in the sense of either oversensitivity to stochasticity or oversensitivity to validity.
But also adaptive learning to different types of.
Yeah.
That's been a big takeaway for me, I think.
I think, yeah, I'm just thinking about
respond. Some features of variability in learning environments is useful and some isn't. That's
yeah.
All right, round of applause for Katie. Very, very tricky paper, Katie. You bit off the right toffee there.
Yeah.
Very well. Thank you very much for digesting it for us. Yeah, see you all soon. Bye. Well done, though. Thanks, Katie. Thanks for taking the time.